Cool. Okay. 301. Let's get. Okay, here we are, week number 8. Technically halfway through the 16-week course and starting up another section. This section is all about optimizing and scaling. So it's a great add-on to the content we already covered. You'll see some things from the prior module reappear again. So some of this stuff will be familiar, but it's all in the mindset of optimization and scaling our VMware infrastructure. Because there are less chapters, I'm actually going to do 1 chapter a week instead of 2. But just as always, you are more than welcome to jump ahead and do the labs ahead and be done with the class early. There is no harm or foul in that. Here's the main objectives for the whole course. Here are the 10 chapters. Today we're actually going to do 1 and 2. And then next week will be just 3 and then 1 all the way to the end. A lot of this stuff you've seen before, like how VMware has put their slides up. Reference sites for you to gain access to. Online resources that are available to you. Quick review of your interfaces. You have your host client, which is the ESXi host, vSphere, and the vSphere web client. Well, again, this is all using the information from last module, the networking. We're going to enter today's talk with the distributed switches, and then we'll later talk about storage and the hosts themselves. And just to make sure I have all my chats up, just in case there's questions. Now, within the hosts themselves, the areas that we'll talk about to optimize. Some security stuff that we'll talk about later on. Of course, this is all part of the VMware paths that already exist. Cool. So network scalability, that's the main topic of today. And we're going to throw our focus first on the distributed switch. As you recall, when we talked about switches, it is much more preferred to use the distributed switch when we have multiple hosts in a data center, because our settings will be able to move across all the hosts. The virtual machines will be able to connect to that same switch no matter where they are. In case a host goes down, the VM is able to move over to another system and continue working as though nothing happened. Our distributed switches have many benefits that outweigh a standard switch if we're talking about multiple hosts in one data center. Now, as you saw in the prior module, your distributed switch can move settings, can move networks around, and the VM will never know that it originally came out of one physical NIC, but because of whatever that same NIC is overwhelmed or it's down or whatever the case may be, its data comes out a different NIC, and life continues on without any issue. Now, your features, your standard switch does not have many features. The distributed switch has a whole lot more. Go figure, it is completely software based, so it has much more flexibility. We can load balance and NIC team our distributed switches. That way, no one NIC card is overwhelmed and all traffic continues flowing smoothly without any bottlenecks. Our switches are capable of the Cisco Discovery or the link layer discovery protocols. LLDP is the vendor neutral. So if you have Cisco switches that are directly connected to your data center, then you probably want to go with Cisco. If you're using other products, you want to use LLDP. In the distributed switches advanced section, you can choose which protocol you're going to use. And you can also choose their mode of operation, either listen, advertise, or both. We can bind ports together, either static or ephemeral. And static is the default setting. If you want to do static, you'll also have the choice of elastic or fixed. So if a port, if all the ports are assigned, it'll create more ports. If it's fixed, it won't do that. This is all again configured at the distributed port group level. Because distributed switches are software based, they're able to do funny little things. And one of these is traffic filtering. For example, we can make traffic rules to either allow, drop, or tag certain kind of traffic coming into our switch, into our virtual switch, to our VMs. And we can define things by IP, MAC address, or system traffic. For example, here there's a rule being made for systems on VLAN 32 with a MAC address starting with 005056. That this traffic will be allowed into the distributed switch in the data center. Of course, we can choose either a specific VM or we can choose quite a number of different ways that the system traffic will be affected. We can mark network traffic with a COS tag for layer 2 traffic or a DSCP tag for layer 3. These taggings can help ensure that packets don't get dropped by the physical network. We can do quality of service and SLA requirements by using these marks. So here's a quick question for you. With a route based on physical link load teaming policy, uplinks in the port group are tested every 30 seconds. If the load on the uplink exceeds 75% of usage, then the VM with the highest input output is moved to a different uplink. And the answer is true. Because load-based NIC teaming is a distributed switch feature that is aware of the load on uplinks and takes care to reduce the load if needed. Something that you don't have to manage, completely managed on its own. As with everything in the VMware world, we have health checks. And we can add health checks into our distributed switches. For example, any mismatched VLAN trunks, any mismatched NPU settings, and virtual switch teaming policies. Here in this example, we have 2 hosts using distributed switch with 2 distributed port groups. And you can see they have some different settings. You can enable a health check in the distributed switch. It is under settings, under health check. Once it runs, it will tell you the health status and what we can do to fix any issues. Because distributed switches are completely software-based, it is possible to back up the configurations, to restore, to create new switches, or revert based on previous, because it's all software-based. We can also export our configurations to a file. And obviously, if we can export, we can also import and restore should something go wrong later. We can also roll back in case of accidental misconfiguration and we lose connectivity. We are able to roll back, either automatic if it's detected and it's configured, or use the DC UI to recover. Rollback is enabled by default, which is a good thing, because if a tech accidentally does something wrong, it can take over and revert back the settings and nobody knew what happened. If you forgot, this is the DC UI, the GUI that you get when you go directly in front of the ESXi with a mouse, keyboard, and monitor. The network input-output control. Will be our next item in scaling and optimizing. Version 3 can do network bandwidth allocation for specific business critical applications and resolve situations where we could get bottlenecks. It'll handle distributed switches across entire resource pools. Version number 3 obviously gives you more capabilities than version 2, so it's always suggested to use the latest. For example, we can set parameters for things that are essential, like management, iSCSI, vSAN, and virtual machines. Configuring these will allocate specific bandwidth for specific traffic. So in this case, we're making a allocation for management traffic. And we're going to reserve 500 megabits out of our total bandwidth of 7.5 gigabits for management and management alone. So with version number 3, we can allocate bandwidth on each physical network adapter. And you can reserve no more than 75% of a physical NIC. So in this case, we have 2 hosts, 4 NICs. Each one of them is 10 gigabit. We can reserve up to 7.5. Useful when we don't have the budget to create multiple physical networks. Of course, vSphere has the capability to show you, after you made a reservation, how much of it is being used and how much is still available. So after some time and you see that your reservation may be a little too big and you can reduce to spread around some of that bandwidth, you're able to do so. We can also make network resource pools, just like we can do with virtual machines and everything else. Of course, this is all using distributed switches. And can use various hosts and NICs together. Creating these pools would be within a distributed switch. Here you see we're making this resource pool and we're going to reserve 2 gigabits. As with everything, we can set our limits and shares for this specifically allocated bandwidth. Of course, with any reservations, just like the resource pools, VMs and whatever is using it cannot go beyond that the maximum for that pool. Bandwidth admission will verify that our hosts won't get overwhelmed. So if we have 2 VMs and we're going to add a third, the part of DRS will verify that if we add this third VM, will it eat up all the reservation we have? And if so, then it's not going to let that VM through. And if we have a down line somewhere, the distributed switch with DRS will be able to move that data around so that the VM stays connected and doesn't feel the difference. Same with HA. Making sure VMs are on all the time. So here's just a quick question. You have the distributed port group named prod1. You want to guarantee that the VMs connected to prod1 can access 25% of the available reserved bandwidth for VM traffic. Using the bandwidth reservation example shown, what must you configure to provide the appropriate bandwidth to the VMs on prod1? And here it is. The aggregated amount is 48 gigabits. 25% is 12 gigabits. So the prod1 resource pool would have 12 gigabit reservation. Final lesson for the day. Other distributed switch features. The link aggregation allows you to connect multiple physical NICs together in uplink port groups that allow interconnectivity throughout a data center. Here's an example of a host deployment with 4 uplinks connected to 2 physical switches. We have our 2 physical switches that connect out to the real world. We have our 4 NICs. We have our link aggregations, 1 and 2, interconnected in to our whole configuration. And even though we have these set up here and these set up here, they're able to communicate with each other. You can create these link aggregation groups in LACP. You can configure them without losing connectivity, which is good because you can do this while the VMs are running, while your infrastructure is up. You can do this on the fly. Then we can assign what uplinks we want into this. And finally, we can set them up in order. And then they'll handle load balancing between those ports. NetFlow is a network analysis tool that'll let you see the traffic that is occurring in a distributed switch. Kind of like your kind of like Wireshark-ish, where you can do profiling, IDS or IPS, forensics, and compliance. It is unidirectional, so it's copying traffic from one direction. You could do it internally or externally, depending on how it's set up. You can send it out to a third-party collector, kind of like TCP dump or something else to aggregate that traffic. There is a NetFlow option that you can configure, and that's where it'll forward out the traffic. You can enable it for a distributed port group as well. It is also possible to do port mirroring through these distributed switches. Just as with everything, it's a setting inside of the distributed switch, and you select what kind of what kind of port mirror do you want. You set any settings that are necessary. We can choose the source and destination. Which direction do we want to capture the traffic? Do we want to capture more than one port IDs? And you'll have a lab to do to set up this and be able to see that on the fly. With that, we have reached the end of chapter 2. Feel free to ask any questions in Discord if you have over this chapter, if you are behind in any of the labs, or if you need any general help. But with that, I will stop the share and stop the live.